Hello viewers, welcome back to our series of lectures on chemical bonding. In today's session, we will take up VSEPR theory to explain the shapes of molecules there. The session is planned as follows, that is, to begin with, we will have a brief review of the contents of the previous session. Thereafter, we will come to the main theme of today's session, that is VSEPR theory, that is valence shell electron pair repulsion theory. We will talk about the postulates of this theory and then see the application of those postulates to predict the geometry of different kinds of molecules there, molecules and ions also. Then thereafter, we will touch upon what are called as polar covalent compounds, and we will focus attention, rather we will limit our attention only onto the diatomic molecules there, and then we will see that how is the percentage ionic character of a polar covalent compound related to the difference in the electronegativity of the two atoms which are bound together there. And towards the end, we will sum up what we do in today's session. Now, let us try to recall what we have done so far. What we have done so far is, we started by introducing the concept of chemical bonding as a process that is accompanied by a decrease in the energy of the system. That is, the two atoms will be said to be bonded if the combined energy of the two happens to be less than the sum of the energies of the two individual atoms there. Thereafter, we gave a historical account, historical perspective of the developments in the area of chemical bonding. Thereafter, we moved on to the main theme of the previous session, that is the discussion on the classical theories of chemical bonding, wherein we took up the Lewis theory of covalent bonding and Cauchel's theory of ionic bond formation there, in terms of sharing of electrons and transfer of electrons respectively. Then we took up and outlined the limitations of these two theories there, and we made a case that these two theories, though do give an idea about the bond formation in terms of acquiring a stable electronic configuration, but they are silent about anything on the shape of the molecule or the molecular geometry per se. And that limitation, we will try to see that how do we get over that limitation in terms of what is called as VSEPR theory. What do we understand by molecular geometry? Basically, if you look at a molecule, we find that in a molecule each atom has a definite position related to other atoms there. Let us look at this picture here. These are different molecules shown over here. That means, other way we can probably say that molecules comes in variety of shapes and sizes there. And this specific three-dimensional structure of a molecule is called as the molecular geometry. And what we are trying to do today is, we are trying to see that how do we explain the geometry of a molecule in terms of the known concepts at this point of time in our argument so far. Now, so far we have just talked about the classical theories. So, with the background of classical theories only, we will try to see that how do we explain the molecular geometry. We will not touch upon what happens as a consequence of the modern theories. We will come to that at a later stage. VSEPR theory, as I mentioned earlier, VSEPR is an abbreviation for valence shell electron pair repulsion theory. Now, all of these words have a significance in this theory here. Valence shell, that means valence shell electrons, that means this theory take cognizance of the valence shell electrons of the atoms there. And then we have what is called as electron pair repulsion. That means the repulsions between these electron pairs which belong to the valence shell of the atoms which are binding together. So, that is what the basic premise of this theory is. And this theory basically is a method which can be used to predict the molecular geometry. And as I mentioned, it is based on their inter-electronic repulsions of the valence electrons. It was proposed by Sedgwick and Powell in 1940, which was thereafter extended by Nyholm and Gillespie in 1957. Now, there are two postulates to this theory. We will talk about these postulates and understand what are the postulates, what do they signify, and then how do they explain the molecular geometry of different kind of molecules there. Let us take up the first postulate. The first postulate says that is the electron pairs, whether they are bonding electron pairs or non-bonding electron pairs, they around the central atom in a molecule, they arrange themselves in space in such a way that they minimize their mutual repulsion. What it means to say is that suppose I have a molecule, I look at a central atom there and try to see that how many valence pairs of electrons are there, and then they will act in such a way that they will repel each other and try to go as far apart from each other as possible there. Let's first understand the meaning of the bonding pairs and non-bonding pairs there. Now, this is Lewis representation of fluorine molecule. This pair of electrons here is the bonding pair of electrons, because this is the one which is constituting a single bond between the two fluorine atoms there, and rest of the electron pairs here, they are the non-bonding electron pairs there. Similarly, for water molecule, these two are the bonding electron pairs. This is the one which is going to form a bond between O and H here and OH bond over here. The two OH bonds are formed in water molecule, and then these two electron pairs which are lying on the oxygen atom there, they are the non-bonding or lone pairs over there. Okay. So, this distinction is very, very important for us. Let us move further and see, take an example here. Suppose I have got a molecule such that the central atom in the molecule has two electron pairs around it. Now, if they are there, let us take this molecule here. Say this is the atom here, and they happen to be, this is one electron pair, this is second electron pair. Now, as per VSEPR theory, what it says is that these two electron pairs, if they are there on the central atom, they will repel each other. They will repel each other in such a way that they go as far apart from each other. That means they will repel to such an extent that these two pairs are diametrically opposite to each other, because for two electron pairs, this is the most stable possible configuration over there, and this basically refers to what's called as a linear geometry. That means if a molecule has got only two lone pairs around this, two bond pairs of electrons around the central atom, then this molecule is likely to be a linear molecule there. Now, if we go further and see what is the second postulate. The second postulate says this basically is the one which becomes operative when we are dealing with molecules which have got central atom having one or more lone pairs. Because if there are only bond pairs as we had in the, then only first postulate is good enough to tell that where would this bond pairs will go. But if the molecules have got the bond pairs as well as lone pairs, then the postulate 2 becomes significant there. And this postulate 2 says that the repulsion between two lone pairs of electrons is greater than that between a bond pair and a lone pair, and which in turn is stronger than that between two bond pairs. That is, we have got this order here, that is lone pair repulsion is greater than lone pair bond pair repulsion, which is further greater than the repulsion between two bond pairs over there. So, this ordering is very, very significant there, because this is the one which is going to determine what is the formal final molecular geometry of a given molecule there. Let us take that the molecular geometry actually, according to this theory, can be predicted on the basis of two postulates. That is what we have formulated here, and on just to make an application of this theory, we need to categorize, to understand, because to kind of organize our understanding of this, the application of this theory, we need to categorize molecules in three categories there. The first one refers to the molecules which have got a central atom having only bond pairs. That is the first category. Second is the molecules with central atom having bond pairs as well as lone pairs. And the third category is the molecules with central atom having multiple bonds as well. So, we will take up each one of them one by one. Now, let us start with the molecules with central atom having bond pairs only. And this is a generalized picture which shows the possible geometries with different number of bond pair of electrons. That means, we have got central atom here, a central atom here, another one here, yet another one here, and so on and so forth. And then around that there are different numbers of bond pairs of electrons. And we have shown that suppose there are two bond pairs here, say a molecule of BeH2, beryllium dihydride, we find that these two bond pairs will be at an angle of 180 degree from each other, and the molecule will be having a linear geometry there. And if they happen to have three bond pairs around that, and they will repel each other in such a way that they acquire the geometry as shown over here, such that these two bonds here, say this is, suppose this atom A, this is atom B. So, this AB and this AB bond will make an angle of 120 degrees. One typical example is BF3, and this will be a trigonal geometry there. And suppose there are four such bond pairs around that. Say this is a central atom here, and there are four bonds there. So they will acquire what is called as a tetrahedral geometry there with a bond angle of 109.5 degrees. That is, we will have a regular geometry which is a tetrahedron, and each of these bonds, say AB bond here, the atom A is the center, B is on the vertices over the tetrahedral here. So this AB bond and this AB bond will make an angle of 109.5 degrees there. Similarly, if you have a system of this kind with the 5 neighbors, then what they acquire is, this is called as a trigonal bipyramidal. That means we have got a trigonal thing here, and this is one pyramidal atom here, another pyramidal atom there. This is again a very important kind of a geometry there. And typically, maybe we can think of PCl5 as one representative species for that. And then suppose there are 6 such bond pairs there, then they will acquire a regular octahedron geometry. Tetrahedron is for when there are 4 bonds there. For 6 bond, it is an octahedron geometry there. SF6 is a typical molecule for that. Now, let us move further and see that if we have got molecules with central atom having bond pairs as well as lone pairs, then what happens? That's the most important thing here. And in such a case, as we know that both the postulates become operative. The first postulate that decides the location of the electron pairs, that is the bond pair as well as the lone pair around the central atom. And this in turn actually gives what is called as a electron pair geometry. That is the geometry which tells about how are the electron pairs arranged around the central atom. Then the second postulate becomes operative, and then you remember the second postulate which says the repulsion between lone pair repulsion is more than the lone pair bond pair, which in turn is more than the bond pair repulsion. So when that becomes operative, we find that this basic electron pair geometry gets distorted, and what you get is called as the molecular geometry. So that is how we try to work out the molecular geometry for different kind of systems. So let's take examples here. Let's take the first case. As I just mentioned, the molecular geometry will depend on the number of shared bond pairs of electrons and also the unshared or the lone pairs of electrons. Let me take the case when number of bond pairs and lone pairs put together happens to be 4. I am taking 3 different molecules here, different species here. Say I am talking about CH4, NH3 and H2O. We find that the central atom in the 3 cases, here it is carbon, it is nitrogen here, and it is oxygen over here. And we find that the total number of electron pairs around the central atom happens to be 4 here. In this case, there are 4 bond pairs here, and we know that 4 bond pairs will give a tetrahedral geometry, and methane is one of the typical example of a molecule being a tetrahedral geometry. In case of ammonia, what do we have is, we find that there are 3 bond pairs there, 1, 2, 3 NH bonds are there, and there is 1 lone pair of electrons on the nitrogen atom. So to put together, so there are total of 4 electron pairs, and here again the electron pair geometry will be tetrahedral, because electron pairs are disposed in the form of a tetrahedral. But when the second postulates become operative, whereby the repulsion between this lone pair and then these bond pairs happens to be more than between the bond pairs and bond pairs, we find that this bond angle becomes lesser. It comes to about 107 degrees as against 109.5 degrees that in case of a regular tetrahedron of methane there. If we go further and look at the water molecule, in case of water molecule, there are only 2 bond pairs and there are 2 lone pairs. The total happens to be 4 again, and then since there are 4 electron pairs, the geometry, the electron pair geometry is tetrahedral. But because of the second postulate becoming operative and this repulsion between the lone pair and lone pair being larger than the lone pair bond pair, which is still larger than the bond pair, we find that the overall geometry of this molecule is basically a bent molecule there. This is trigonal pyramidal. So in terms of electron pair geometry, all the 3 molecules shown over here are tetrahedral. That is, all molecules have here tetrahedral electron pair geometry, but the molecular geometry, this is tetrahedral, this is trigonal pyramidal, and this is a bent molecule there. So we find that the actual molecular geometry will be decided by the 2 postulates both becoming operative. First postulate gives me the electron pair geometry and second postulate gives me the molecular geometry. Okay, let us move further and take another series of molecules here. Say this one, the number of examples here, we find that in this case the examples taken are such that the number of bond pairs and the lone pairs, the sum of the 2 happens to be 5. Now let's take the first case, say PCl5. In PCl5, we find that there are 5 bond pairs. So 5 bond pairs, 0 lone pair there. And we find that this molecule has got just the first postulate is operative here, second is not required because there is no lone pair in this. So the geometry is trigonal bipyramidal. But if we come to a molecule of SF4, in case of SF4, we find that there are 1, 2, 3, 4 bond pairs and there is one lone pair here. Now this lone pair has got two possibilities. It can be either on this side or here or here. There are 5 possibilities and these 3 are equivalent here. These are called as equatorial positions there, and these 2 possibilities, the one upwards and the downward, they are called as axial possibilities there. And typically equatorial position is energetically favorable, so it is a preferred orientation. So in case of SF4 molecule, we find that if you look at the electron pair geometry, it will be again trigonal bipyramidal like PCl5, but because of firstly this lone pair occupying the equatorial position and then the consequences of the repulsion between these, we find that this molecule has what is called as a seesaw shape. So that is the kind of a shape we have. If you look at bend the molecule, it looks like a seesaw here. If you look at the molecule of BRF3, what you find is there are 3 bond pairs and there are 2 lone pairs. Here again total number is 5, so electron pair geometry is trigonal bipyramidal, but the molecular geometry comes out to be just T-shaped there, because when you find it that the molecule will be this is the T-shaped molecule over here. Similarly, if you go further, look at the I3 species there. In this case, there are 2 bond pairs and 3 lone pairs there. So 2 bond pairs and 3 lone pairs. Lone pairs preferably, as I mentioned earlier, will occupy the equatorial positions and they will be on this side, and this molecule now, this is iodine here, another iodine here, another iodine here. So this will become a linear species there. This is not a molecule, this is an ion there, because VSEPR theory is operative for molecules as well as for ions as well. Let us go further and look at this. Basically shows that equatorial position is energetically more favorable than the axial position there. Now suppose we got yet another series of molecules, that's a species, because these 2 are molecules, this is an ion here. We find that here the number of bond pairs plus lone pair happens to be 6, say SF6, all are bond pairs, geometry is octahedral. So the electron pair geometry as well as the molecular geometry both happen to be octahedral. Whereas in case of IF5, now what you find is that in this case there are 5 bond pairs and 1 lone pair, and we find total of 6. The geometry to begin with, the electron pair geometry happens to be octahedral, but because of the second postulate becoming operative and the repulsion between the lone pair and the bond pairs being more than the bond pairs and so on and so forth, we find that this molecule has a square pyramidal molecular geometry. So we find that this is a square here and this forms a pyramid on this. If you move further, we are F4 minus. Now I think you can explain on your own also. That is, in this case, since there are 4 bond pairs and 2 lone pairs, so the bond pairs are like this, and because of the repulsion to begin with, the electron pair geometry is octahedral because there are totally 6. But because of the second postulate becoming operative, we find that this molecule has got a square planar orientation there, because when there are 2 lone pairs, they will acquire any 2 because the octahedral is a regular thing, a regular shape. So any these 2 lone pairs, these 2 positions, or these 2 positions, or these 2 positions, all are equivalent. So any 2 opposite positions will be occupied by the lone pairs, and rest 4 will be the ones which will be by the bond pairs, and the ion will have a square planar geometry there. Now let us look at the molecules with central atom having multiple bonds. In case the central atom is bonded to other atoms by multiple bonds, we find that the electron pairs for the multiple bonds, they occupy more space, they are larger in size, and typically the electron pairs of a triple bond occupy more space than that of the double bond, which in turn occupy more space than that of a single bond. Let us look at this. Now you find that this is HF, single pair of electron, and then here in this case it is a double bond. So there are 2 electron pairs there. Here it is a triple bond, 3 electron pairs there. So this is occupying much larger space as compared to this, which is in turn larger than this one there. But according to VSEPR, a multiple bond behaves as a single electron pair. That means only thing is the electron pair is of larger size, which has its ramifications, but otherwise in terms of predicting the geometry, it behaves as a single electron pair. So, that is a very, very important thing we have to take note of. Let us take some examples here. So, look at molecules of beryllium difluoride, carbon dioxide and hydrogen cyanide. We find that all of them are linear, because in case of beryllium difluoride, we find that there are 2 bond pairs here. In case of carbon dioxide, so this is a double bond, so is this one. But here we find that in terms of determining the geometry of this, we find that it is linear again. So, whether we have got 2 double bonds like this or got 2 single bonds, the geometry happens to be same. Whereas in case of HCN here, we find that this triple bond also is behaving as a single bond only, behaving as a 1 electron pair, and then we find that geometry again happens to be linear. So, the molecular geometry is determined by, in these molecules, the first bond pair, and the second and third electron pairs in the double and the triple bond do not affect the molecular geometry. That means, basically, in order to work out a geometry, probably we have to just talk about, think of only 1 electron pair here, 1 electron pair here. So, since there are 2 electron pairs, they will go opposite to each other and the molecule will be linear. Same is true over here. Let us take yet another example here. Let us take the example of, say, formaldehyde. In case of formaldehyde, there are 3 effective electron pairs, and as a consequence, the molecule has a triangular shape like BF3. This is my molecule of HCHO, formaldehyde. We find that this is carbon, this is oxygen, it's a double bond here, this is single bond, a single bond here. And in this case of BF3, all the 3 are single bonds here. This is a triangular shape here, so is here. But this is a regular triangular shape having a bond angle of 120 degrees we know of. But in case of formaldehyde, we find that this angle becomes slightly larger. It is about 121.8 degrees, whereas this bond angle is 116.5 degrees there. This is becoming so because this double bond here is made up of 2 electron pairs, it is larger in size. So, this repels this to a larger extent, this also. As a consequence, this bond shrinks from about 120 degrees to about 116.5 degrees. So, that is the shape wise, this is triangular in shape, but the bond angles tell the effect of this double bond over there. So, the bond angles are not equal as in case of BF3, and secondly, the electron pairs in carbon oxygen double bond, since they occupy more space, they compress the FCF angle there. Let us move further and come to what are called as polar molecules. Let us understand what is a polar molecule. In case of diatomic molecules, any homonuclear diatomic molecule will be non-polar. Homonuclear means the 2 atoms are identical, and when we have got heteronuclear molecules, they will be polar. That means that heteronuclear are when the 2 constituent atoms are different. Let us look at this. This is hydrogen molecule. 2 hydrogen atoms are bonded together. This is HF, hydrogen fluoride here. We find that this molecule is different from this one because this is homonuclear. Now, if you look at, these are the electrostatic potential maps, which I am sure that we discussed about this in another series of lectures earlier. That is, this basically represent the charge distribution on the molecule there, and the grading is such that blue color represents lower charge and red indicates a larger charge. And we find that in case of HF, what happens is, since fluorine atom is highly electronegative as compared to hydrogen atom, so this the bond pair of electrons here, which is a shared pair of electron, it gets shifted more towards the fluorine atom. As a consequence, it acquires some kind of a negative charge on that, whereas this becomes slightly positive there. So, there is a charge separation there, and that is indicated by this kind of a electrostatic potential map. So, this is a positive part of the molecule, this is the negative part of the molecule there. In other words, we say HF is a polar molecule. It is a polar covalent molecule, whereas hydrogen molecule, since both atoms are identical, it is a homonuclear system there. So, there is no charge separation, it is a simple non-polar molecule there. So, basically what we infer from here is, that is, the polarity in a molecule is coming because of the difference in the electronegativity of the 2 constituent atoms there. Let us look at this picture. What you find is, we have got HF, HCl, HBr, HI. What you find from here is, that is the difference delta E value of electronegativity, delta electronegativity. In case of HF is 1.9, fairly large, 0.9 here, 0.7, 0.4. Now, what you can see, these are very glaringly obvious pictures here. You find that here there is an enormous amount of charge separation. This is highly red here, this is highly blue. Whereas in this case, this is not much different from what we had in case of hydrogen molecule there. There is a slight shift in the charge here, but not as significant as in this or in this, and so on and so forth. So, you find that, so we start from here. So, delta electronegativity is just 0.4, there is a slight charge separation there. Here it is more, still more, still more. Or in other words, we can say higher the delta electronegativity, greater is the polarity of the molecule there. Now, we can see from here is, that is, the polar covalent compounds have what is called as a partial ionic character, because since there is charge separation, they start behaving little ionic in nature. And we have just seen that the polar covalent compounds have got partial ionic character. Let's see how do we rationalize this partial ionic character in terms of the difference in electronegativities of the bonded atoms. And this graph is a typical graph which is very common, which gives you the variation in the percentage ionic character of a diatomic molecule and delta En, that is the delta electronegativity here. For a very low delta En, say about 0.3 or so, from 0 to 0.3, this refers to non-polar compounds there. But as delta En increases, we find that the percentage ionic character increases in the following fashion here. That's one observation we had. Second observation is that if you look at this 50% ionic here, if you draw a line like this, come over here and come down, we find that we get a value of about 1.7, which means that if delta En happens to be 1.7, the molecule happens to be about 50% ionic in nature. So that is the kind of a line of demarcation here. That is, any value less than 1.7, it will be covalent here. So as we go farther and farther from this, we get more and more covalency here. As we go in the opposite direction, as delta En increases more and more, it becomes more and more ionic there. That's second observation here. So on the basis of this, we can have this kind of a simple kind of a classification, that is, delta En value of greater than 1.7, typically the molecule will be having more ionic character than the covalency in the, and as delta En increases more and more, it becomes more and more ionic in nature. From about 0.3 to 1.7, we have got polar covalent molecules there, and a value of less than 0.3 of delta En indicates that the molecule happens to be non-polar covalent here. Now, this partial ionic character actually can be determined for a given molecule on the basis of the measurement of its dipole moment, which we will be taking up in the next session there. Okay. For today, let's sum up what we have done today. What we have done today is, we started by reviewing the contents of the previous sessions, and thereafter we explained the premise of VSEPR theory and used it to predict, rather to talk about the geometry of different kind of molecules, and we made a very clear distinction between two things, two very important terms, that is the electron pair geometry and the molecular geometry. Electron pair geometry tells about the disposition of electron pairs, whereas molecular geometry tells you the final overall shape of the molecule. Thereafter, we came down to the polar covalent compounds. We talked primarily about the diatomic molecules there, and we found that the kind of polarity or the polar nature of this depends on the delta En values there, and we try to rationalize that relationship between the percentage ionic character and the difference in electronegativity. In the next session, we will continue from here and see that how do we determine the percentage ionic character of a bond in a molecule on the basis of the measurement of dipole moment. And also we will transition to the modern theories, and we will start with the basic premise of valence bond theory. Thank you.